right, why don't we go ahead and get started. So welcome everybody to E16A. Just for those of you who don't know me, my name is Eleng. Vladimir had to take some important travel today, so he asked me to fill in. I'm one of the folks that have been working on or teaching this class for a little while. And Vladimir's done me plenty of favors, so now I'm returning it by being here today. Actually, thank you all for being here. I understand you have a midterm tomorrow. So obviously what I'm talking about here is not directly in scope, but certainly is kind of building on all the stuff you've learned already. And also certainly will be covered on the final, so you're doing yourself a favor as well by being here. In case you want to reach me afterwards, this is my email. It's just my first name at berkeley.edu. And pretty easy to find from that particular perspective. Okay, so maybe before we get going, any questions on sort of material and everything so far, at least particularly in this module? Maybe I should ask it a different way. How many folks feel like they're ready for the midterm? All right, so I guess there's going to be a whole bunch of cramming going on later tonight, even in this crowd. All right, so in terms of what we're going to cover today, basically kind of the last thing that we wanted to do in this module, which I think you've seen hints of or sort of simplified versions thereof several times throughout, is really just kind of go through and do one really kind of more complex design example. Okay, so that's really kind of going to be the focus of the lecture for today. And the specific design example we're going to do is to build a current source. Okay, so I think Vladimir might have mentioned to you many times before that voltage sources, in terms of physically implementing them, kind of are easier, and that it's basically just a battery, so you get that kind of for free from chemistry. Turns out building actual current sources is a bit more involved. Okay, so that's the example that we're going to do mostly here today. Now, as it turns out, as you all hopefully know very well, current source was something you actually used fairly directly in your touchscreen lab, right? And in fact, if you haven't done it already, I think you're doing it either this week or next. So we're going to show you sort of how we're going to take the current source that we implement and then really actually integrate that in with the rest of the touchscreen sensor that we've been talking about, again, kind of throughout almost this entire module. So everybody with me on sort of the plan of action here? Okay, good. So just first things first, let me kind of give a little bit more specificity as to what the actual design problem I want to solve is. So what I want to do here is I'm going to state the design problem as being build a current source using only op amps, resistors, and voltage sources. Okay? Now, I believe you guys have already learned about the design procedure that we've set up for everybody. So just maybe as a reminder more than anything else, what's step one of the design procedure? Yeah, so you said it as specifications. Maybe to say that, at least in the way that I like to think about it, step one is really just clarify what your goal actually is. Okay, make sure you understand what in the world it is you are really trying to do. Because as hopefully you've heard about before, and if not, then I'm going to say it here. Turns out that, the large majority of problems that people have in the real world with the designs that they build is they misunderstood what their goal was in the first place, okay? Or person A thought it was X and person B thought it was Y, and, obviously at the end of the day, when you put things together, it doesn't actually work. Okay, so let's go ahead and actually indeed do step one, which again is restate the goal. Okay, and that's the point there is just to make sure that you understand what it is you are really trying to do. So from that perspective, if my goal is to build a current source, from a sort of IV characteristic standpoint, what does that mean? What is the defining sort of behavior of a current source? Yeah. Bingo, exactly. So if I want to build a current source, I want to build a circuit that creates a constant current through the output terminals regardless of what that voltage on the output terminals is. Okay, that's really what we mean now by building a current source. Now, to be clear, we have to do this obviously only with op amps, resistors, and voltage sources, but hopefully from the original problem statement that was also somewhat clear. Okay, so this indeed, when we say we want to build a current source, it just means, all right, we have this thing that and I'll just kind of draw it as a magic box here. There'll be some magic box that has two terminals sort of as its quote-unquote output. And what we're saying is that regardless of what voltage we put across that, we want to make sure that the current flowing is going to be constant. All right? That's essentially what a current source actually is. So this is what we have to have our circuit actually implement. Everybody good with this? All right. So, again, maybe as a reminder more than anything else, what's step 2 of the design process? Now that we've restated our goal, what's the next step? Yeah, we have to come up with some kind of a strategy, right? Okay, so here actually is typically where a lot of the creativity ends up coming into the picture, because we have to take sort of this, specification written in words and figure out, well, okay, how can I actually do something like this? Okay, so from a strategy standpoint, turns out there's actually nothing really particularly quote-unquote magic we're going to be doing here. The magic is going to come more in how we really implement it, and you'll see why I say that in a second. But the basic strategy is kind of simple, all right? So if you think about it, one of the first things we learned was just Ohm's law, right? And Ohm's law said that, for a resistor, if we looked at the voltage across that resistor, that was just the current times the resistance, right? Okay, so why did I mention this? Well, our goal, as I said, was to create a constant a constant current. So if I just restate this is saying that if I can create a current as just being some voltage divided by some resistance, and I can make it so that the voltage and the resistance, both, their values don't change, then great, I'm done, right? Like, magically I have a constant current, because it's just set by the voltage and the resistance, and both of those are constant. Okay, by the way, to be clear, all of this is going to sound a little bit weird at first, and this is perhaps something you may or may not have seen before. Actually, I think you have. As usual, we're going to make a first attempt at something that's based on this simple idea. We're going to build it. It's not actually going to work, but it's going to give us inspiration for what are some of the problems we need to solve, and therefore, how do we actually going to take the step that will get us to something that really does work. All right? So if our strategy is to just, somehow leverage Ohm's law, let's do kind of the simplest, stupidest version of this. Okay? So the simplest, stupidest version of this would be to say, all right, well, if I have a voltage source, some, let's say, Vs, and some resistance, let's say Rs, let me try and take kind of that black box that I drew before and just build it like this. And then say that, all right, the output is over here, right? So there's some VL and some IL, right? So this is going to be kind of my first attempt at building a current source. Now, just to jump ahead a little bit, is this going to work? No, of course not, right? This is by no means a current source. This is a voltage source with a resistance in series. But just to be absolutely clear and to do a little bit of a review here, right, the reason this won't work is that, remember, we said that our goal was to make it so that the current was independent of the voltage. So now let's explicitly sort of do this as part of our design process. Right, so step 3 was always that once we had a kind of, I actually skipped a step here. So this was step 3, which was to implement it. And then step 4, is to verify. Okay, so now let's check, is this actually going to work? As we said, it's not going to work, but let's just formally do that here. So why is this not going to work? Well, we need to check, is IL independent of VL? Okay, so now we can just go and actually analyze the circuit that we drew. Okay, and I'm going to draw the whole thing, but I'll define where the ground, where I decided the ground to be in 1 second. Okay, so I'm going to call this ground here. Let's call that U1. Let's call that over here U2. And I'll draw the IL over there, but hopefully it's obvious that IL is also what would have to go through the VL if you actually connected something over there, right, just by KCL. Okay? So, again, hopefully this is all kind of secondhand to all you folks, and if it's not, this would be a really great thing to figure out by tomorrow, because trust me, this will certainly, be useful. So, hopefully it should be obvious that if I've defined this here as being ground, U1 is just equal to Vs based on the characteristics of the voltage source, right? That is what a voltage source does. It just fixes a voltage drop or rise across it. Okay? All right, now hopefully it should also be clear that U2, just by the way I've defined things, is equal to VL, right? Just because I defined that way. Okay, so the next thing I can do is actually use Ohm's law. I can say that IL, which is the current flowing through that resistor, And let me just label the plus and minus to make sure everything is clear. Actually, I'll do it the other way. Right, so Ohm's law would say that U1 minus U2, which is the voltage across the resistance, is equal to IL times RS, right? Okay, so now let's just plug everything in. So this says that IL is equal to VS, which is U1, minus VL, which is U2, divided by RS, right? Okay, so now this is where it should hopefully be, once again, obvious. This doesn't work, right? Why? Because IL certainly is not independent of VL. If you change VL, IL will change, right? All right, so here's where kind of the magic trick is going to come in. And this is where I'm going to maybe kind of like turn things around a little bit to you folks and see if we can get some ideas out of the class. So we're basically saying this doesn't work, right? No good. But what if VL somehow was constant? Okay? Like always had some known value. And in particular, what if VL somehow I magically made it 0 volts? Okay? Well, if I did that, then that would say that IL would just be equal to VS over RS, right? So that looks pretty good. That doesn't depend on VL, but it doesn't depend on VL because I said VL has to be 0 volts. So why do I bring this up? Well, what this is kind of giving us a hint towards is it's saying if we somehow can come up with a magic method where, from the perspective of this circuit that I tried to build, the VL that it sees is 0 volts, but I still am able to get this current to flow and somehow make it to the output, then magically I will have actually implemented a current source. Okay? So this sounds like a really, really weird thing, but turns out you have actually already seen this circuit, you just don't know it. All right? So, taking, like your creative hats now, or maybe let's say you're attempting to link things together hats, where have you seen circuits where, you could basically say, all right, I know that I can make some particular node voltage be equal to a constant value, and in particular, usually to 0 volts. What's something you've actually analyzed quite a bit that, had this kind of nice behavior to it? Yeah, op amps, right? So in particular, in which case was it where you could use an op amp and you could say that, one voltage or one, let's say, potential had to be equal to 0 volts? Yeah, exactly. So just generically speaking, right, when we took some op amp circuit as an example, and we had, the V plus and the V minus there, right, as long as we connected this whole thing such that one way or another, there was feedback from the output back to, in this case, the negative terminal, meaning the overall circuit was in negative feedback. Right? Golden rule number 2 said that V plus equals V minus, which would mean that V minus has to be equal to 0 volts. Okay? So why do I bring this up? Well, that means that basically if somehow I can take this circuit and connect U2 to some kind of op amp in negative feedback, I can make it so that the voltage seen basically at this U2 indeed will be 0 volts, right? And so now the question is just, well, okay, but how does the rest of this really work out, right? How do I actually get this thing to sort of behave as this current source? Okay, well, so let's actually take a stab at it. Maybe I'll even turn it around and ask you folks. So this is our VS. I'll draw it as ground here. This is our RS. What we basically just said is we want this node here to end up as being 0 volts, but we don't actually literally want to connect it to ground, right? Because if you literally just connect it to ground, then you don't actually have an output, right? You've just shorted the whole thing. Okay? So we're going to connect that to this op amp over here. Okay? And it turns out we're basically almost done. The only thing left to do is to say, well, look, I need to somehow take the current that was going to be flowing through this RS and get that to show up as the current through the output, right? And remember, the output is just 2 terminals. Well, so the way I'm going to do that is I'm going to just take a wire, draw it out over here, and now call this the output. So to be clear, this whole thing is kind of like my black box that implements the current source. Okay? Now, to turn this around, and I kind of did this for you, so I want to make sure it's clear why it is that this works the way that it does. Why is it that I'm saying that, if there's some kind of element connected over here, let's pretend it's a resistor, but doesn't really matter what it is, almost. Why am I saying that if there's some current, let's say IL over here, why am I saying that that same IL should show up over here? Why is that true? Yeah. Yeah, exactly. So remember, the other sort of golden rule was that I plus equals I minus equals 0, which you said as the op-amp sort of looks like an open circuit. Both of those statements are equivalent, right? So that means that this current here is indeed 0. So if there's no current flowing here, the only place this current can flow is through there, right? Okay. And indeed, that is exactly the sort of property that we're going to rely on. All right, so it turns out from the design problem, we're quote-unquote done. This is actually it. But let me just go ahead and, sort of one more time, formally verify this, just, make sure it's clear to everybody. Okay? So I'm just going to redraw the circuit here. I've got my VS. I've got my RS. I've got the op-amp. And this is what I'm going to call my output. That's going to have some VL across it, right? Okay, well, so just analyzing it, and again, remember what we want to do is check if, and let me go ahead and label it. So this is IL, which as we said a second ago, this is also going to be IL. Check if IL is independent of VL. Okay? Well, if the op-amp is in negative feedback, which I'm just going to write as NFB because I don't want to write the whole thing out. And then we label this over here. Let's call this U2. Then U2 equals 0 volts, right? If U2 is 0 volts, then as we did before, IL is simply equal to VS minus 0 volts divided by RS, which of course is equal to VS over RS. Great, it's independent. Indeed, this should work. Okay, so in terms of our original goal, am I absolutely totally done? Did we do everything, or are there some caveats we have to be careful about now? In other words, can I take this circuit and connect it to absolutely anything else, and no matter what I connect it to, it'll always behave as a current source? What do you guys think? Yeah. Okay, so you said there's still the constraint of VDD and VSS. That's absolutely true. In other words, if somehow, what you're trying to do over here implies outputs from the op-amp that are outside of its rails, things are not going to work. That's absolutely true. I'm not going to worry so much about that, and I don't know if Vladimir did things this way, but usually when I draw pictures like this and I don't explicitly tell you what the supply rails are, the assumption is that they're large enough that for anything that you care about, you're never going to hit that constraint. But you're absolutely right, that is indeed a constraint. There's two others that I think are, let's say more, maybe not more important, but they're more what I had in mind. Yeah. Okay. So your question actually is very much related to what I was getting at. Okay? So notice I made this statement here, if the op-amp is in negative feedback, right? So it is not at all the case that I can put anything I want here and still have the op-amp be in negative feedback. In fact, as you just said, hey, if this is like an open circuit, well, there's no feedback, so the thing doesn't actually work, right? So this is indeed kind of the first and important caveat, okay? So when I say caveat, what I mean here is that, we mostly met our design goal, but there's two things we have to be careful of that if they're not satisfied, the design actually will not work, okay? And that first one, indeed, is exactly that the op-amp must be in negative feedback. Because again, if it's not, you don't get to use golden rule number 2, and therefore, this U2 will not actually be 0 volts, it'll be something else, and now the design doesn't necessarily actually work the way we want it to. Okay? There's one other caveat which is a little bit subtle, but as we'll see when we kind of put everything together, will actually turn out to be important. Okay? So what's the other caveat that we have to be, careful about here? give you guys a hint. Look at U2 and look at how it's connected relative to the output. So what did we say is the value of U2 when we actually hook this whole thing up? Yeah, it's 0 volts, right? Okay, so if U2 is 0 volts, that means that over here, this also had better be 0 volts, right? Okay, so that may not seem like it's all that important, but trust me, it's going to matter. Okay, and again, we'll see that when we actually connect this whole thing together into the larger touchscreen circuit. Okay? So in this case, U2 has to equal 0 volts, which may have implications on the rest of the circuit. So as I said, this one's kind of subtle, and it's a little bit hard to see sort of in general. But we're going to go through an example, and you'll see why it is that this is going to turn out to matter. All right? Okay, so I think all right. So let's just do actually one specific example. So remember, I claimed that you guys actually already saw this circuit before. So just maybe based on this picture right here, can anyone give me an example of what you might connect across VL over here? Yeah, a resistor. Okay, so let's go ahead and draw that. And I'm going to draw it intentionally in a way that you have not seen before, and then just make sure everyone's clear on what it actually turns out to be. Okay, so let's say there's some RL over here, right? And again, like the current source, everything here on the left is the quote-unquote current source. And the thing on the right is just the thing that we're connecting across the current source to sort of check, does it still behave as a current source? Okay, but before I go any further, what kind of circuit is this? Yeah, it's an inverting amplifier, right? Usually we just draw them slightly differently. Usually we draw them like this. Oops. RL, right? Usually we draw them something like that, or the output is over here. Okay? Well, notice it's actually the exact same circuit. And for those who don't see this, right, the box is just like this in that picture. Let me get rid of this stuff so it's not confusing. Right? So all along, and in fact, when we analyze the inverting op-amp, or amplifier, I assume that the way you did the analysis was you said, okay, well, I invoke golden rule number 2. I see that this is 0 volts. That means that the voltage across this resistor is just Vs. That means that there's a certain current, IL, flowing through here. That current flows through this resistor. And from there, you directly compute what the voltage at the output would end up being. Right? So notice you actually already built this current source and used it. You just didn't realize that the way you were sort of building that, this amplifier to have this gain the way it did was by actually just creating a constant current and have that current flow through some resistor at the output. Okay? Does this make sense to people, or? Yeah. Oh, so it's not that I have a specific reason that I want a resistor here. It's more just that I'm saying that I argued that this whole thing here is supposed to behave as a current source. Okay? So if it does behave as a current source, then whatever behavior I would have expected from just doing something like this, like with a, let's say, ideal current source, hopefully I'm going to get the same behavior here. So my only point was that indeed, you actually do have that same behavior. It's just that it turns out you've seen this kind of circuit before under a different name. You actually analyzed it and saw that this behavior happened. You just weren't explicitly, that fact wasn't explicitly highlighted as, yeah, I can kind of model this whole thing as being a current source of the resistor. That was the only point. Yeah. Other questions on this? Yeah. Okay. So the question was, why is it that sort of, keeping these things... Well, let me phrase it in a slightly different way, and this is not exactly the question you asked, but I think it'll answer your question. So the last part of your question was, well, hey, can't I, change Vs, and wouldn't that change the current? And the answer is yes, absolutely it would. So in fact, that means that I've built something slightly more sophisticated than my original goal, because my original goal was just to build some current source with some fixed value. Now, if you have a way of changing Vs, you can actually change the value of the current source. So in other words, I'm going to turn your question was like, oh, it seems like this doesn't work. I'm actually saying, yeah, that actually does work, and it's even better than what you originally were trying to do. Make sense? Or cool. More questions? Okay, so just to prefetch a little bit, if we're interested now in using this in the context of the touchscreen, instead of a resistor, what do you think you're going to end up connecting across this quote-unquote current source? I think I heard a few people say it. Maybe just somebody raise your hand and speak up louder. Yeah. Yeah, a capacitor, right? So remember, the whole touchscreen sensor, at least the latest one that we looked at, was all based on some equivalent capacitance that was going to be changing as a function of whether or not your finger was pressing, right? And so indeed, rather than connecting a resistor, what we're going to end up doing is taking this quote-unquote current source and connecting it to a capacitor. Now, so here's the question for you folks before we go any farther. If we do things that way, remember I said this whole thing has to be a negative feedback for it to work. Okay? So when I connect the capacitor, is it still a negative feedback or not? So actually, maybe I'm going to have to do this. Let's have everyone turn to your neighbor and talk about that for a minute or two. And I don't want actually just the answer of is it a negative feedback or not. I want you to also be able to explain how would you go about checking that. So go ahead, talk to your neighbor, and let's come back and reconvene in a minute or two. Okay, so how many groups think they know whether or not it's still a negative feedback? Raise your hand. How many people are still paying attention? Okay, who wants more time? Only one or two people. Okay, so there's a lot of talking, but not too many hand raises. Is it too early in the morning or something? All right, anyone want to hazard a guess? Or? Sure. Okay, you basically gave the right answer. So let's partition this into two pieces, right? So first you said, yes, I believe this is still a negative feedback, right? And so let's actually just go and draw sort of the circuit to actually make sure that, we can check. All right? So what we're basically saying is that we're going to take this capacitor and we're going to connect it kind of across the op amp this way, right? That's effectively what we're saying here, and I'll add in the plus and the minus. Okay, well, so in general, what was the procedure you would use to check for negative feedback or not? What was kind of the, the somewhat silly but catchy name that we used for it? I assume Vladimir used this, at least I hope he did. Okay, so did he mention dink and move or dink and check? No? Oh, he didn't. All right, I guess not. All right, so what did he call it? What was the procedure he called for? He just said check for negative feedback? All right, fine. All right, so then I'll explain why I referred to it that way. That actually came from him, so I'm surprised he didn't use it. Okay, so I assume he told you that what you'd basically do is you'd say take all sources in the circuit and set them to 0, right? Kind of like you do with superposition. So if we do that, then this Vs would just go away. We would have an RS over here. We'd have the op amp. Oops, sorry. And we have the capacitor. Right? Okay, so then the next step was you would effectively just take the output and quote-unquote yank on it, right? Like you'd hypothetically say, well, what if the voltage at the output moved, as in this case, up, right? And then what you did with the procedure was you tried to track through, okay, well, if this thing somehow moved up, what would happen back at the input side of the op amp? And based on that, what would then come back to the output? And if it comes back in the opposite sign, then you're in negative feedback. If it comes back with the same sign, you're in positive feedback. And if it doesn't make any change at all, you're like in no feedback, right? Hopefully this sounds familiar to everybody. Okay, well, let's actually go and sort of do that exercise here. So if this sort of, let's say, voltage, or let's say I really should say potential relative to ground moves up, right, then what you're doing is you're actually changing the voltage, or you're trying to change the voltage across the capacitor, right? And remember, the only thing we know about capacitors is there's some like I equals C dV dt, right? That's kind of the basic relationship of the capacitor. Okay, well, if this is the basic relationship and I try and do something over here to change the voltage, that means some current has to flow, right? Well, that means that basically if there's some current flowing, this current has to go through the capacitor and into the resistor, right? And so notice if I move this voltage up, which is just another way of saying if I define VC this way, that I'm increasing VC, right? If I'm increasing VC, that means that current has to be flowing into the capacitor. Because again, passive sign convention still holds, all right? So if the current's flowing into the capacitor, well, guess what? That same current through the capacitor has to flow over here. We know it can't go into the op amp, so it has to go into the resistor over there. Well, so if I have some positive current flowing into the resistor like this, that would say that V minus also is increasing. Right? Well, if V minus is increasing, what does that say would happen at the output of the op amp? Which direction would it go? Would it go up or down? Yeah, I see a whole bunch of people making the hand motion. Exactly, it goes down. Okay, so indeed, this whole thing is still in negative feedback. Yeah? Yeah, so this is where maybe the arrows may make it look a little bit confusing. Notice I defined the plus on the VC here and the minus there. That means this voltage defined this way is increasing. Okay? If that voltage is increasing, just take this whole thing, by passive sign convention, the arrow of the current has to be flowing into the plus. Right? That current would be positive, and if you just follow, if I have an arrow going up here, it has to make a left turn there. Right? And then at this quote-unquote junction, it has to be going down. So let me just explicitly draw that. Then when I hit this junction, the current flowing into the minus terminal is 0. So the only direction it can go is to the left over there. Right? So that would mean that, again, by passive sign convention, if I put the plus here and the minus there, relative to ground, this node, which I used to call, U2 before, has to be going up relative to ground. Does that make sense? Or? Yeah, and this is, by the way, one of those cases where, and in general, right, with all of these circuits, a lot of times it's, you look at something and at first you think it should be going a certain direction. Just be really careful to sort of label everything with the arrows and the passive sign convention and follow it through, and you'll get the right answer. Yeah. Yes? Yep. Okay. So this is a good general question. So your question was, but I'm a little bit confused because we said that in order for the whole thing to work, the top part, the U2 node here has to be at 0 volts. But I just said that the U2 is somehow changing and increasing and causing something to go back at the output. So remember, when you are checking for negative feedback, golden rule number 2 can't hold yet. Right? Because you don't know if you're negative feedback or not. So when you're doing that check, you can't invoke that U2 is 0 volts because you don't know that actually negative feedback has happened yet. So here what you're doing is sort of a quote-unquote incremental analysis of, all right, if I don't know whether or not there's negative feedback, I need to check what is the influence of a change at the output, going back through the op amp and coming back to the output. So that's why I'm allowed to say that U2 here is not necessarily strictly 0 volts, because golden rule number 2, I've not actually verified that I'm in the conditions that would make that make sense yet. Does that make sense? Yeah, so, and again, this is a kind of a good general question, because when you are checking for feedback, both the sign of it and whether or not it exists, there you can't invoke golden rule number 2. Right? Golden rule number 1 still holds. Number 2, you don't actually know yet. Good. More questions? Oh, I see somebody. Oh, there we go. Yes. Okay, so the question was, if the capacitor is quote-unquote charged, meaning it had some initial voltage across it, will this whole thing still work, right? Okay, well, notice, all I did was, I never told you anything about what this voltage initially actually was. All I said was that I'm going to take it and move it up relative to ground, right? So if all I'm doing is I'm saying, well, this moves up relative to ground, notice the current is related to the change in voltage. It's not related to what the absolute value of the voltage initially was. So because of that, yes, it technically, other than what was brought up before about, the limited supply range of the op amp itself, technically whatever this voltage is, as long as it's not outside of the range of the op amp, you're still in negative feedback. Because it's all about just the current is being created by the change in voltage at the output. It's a good question, though. Other questions? Yes? Oh, what you mean in this case where I'm checking for negative feedback? Yes, sure. So the question was, why is it that U2 goes up? Well, remember, the procedure we use is we say arbitrarily somehow, through some magic fairy that, came from the outside world, I take the output of the op amp and I cause it to change. Okay? In this case, I decided that I'm going to change the output of the op amp to be moving up, meaning the voltage is increasing relative to ground. Okay. So the logic or the argument that I'm following here is to say, well, if this moved, that means the voltage across the capacitor also had to change. Right? If the voltage across the capacitor had to change, that means there had to be current flowing through that capacitor. If there had to be current flowing through that capacitor, that current has to flow through the resistance. If the current flows through the resistance, just by Ohm's law, U2 also has to change. Does that make sense? Yeah, no, by the way, to be clear, there are many, many ways one could solve this problem. This is just the one that, let's say, is the easiest and fastest to explain in lecture. You could set up a full, you could do the full, let's say, linear algebra approach that you've seen before of just defining each independent node, write a set of equations, and then just solve. Trust me, you will get the same answer. This is just much faster to explain, here in lecture. So I think that was the question that was asked over here. The short answer is no. And the reason for that, again, just has to do with the fact that the reason the current flowed in the first place is that it's related to a change in the voltage. So if I change the voltage, regardless of what the initial point was, that's what's going to cause the current. Okay. Question in the back, or no, it looks like just yawning or stretching. Okay. So if there's no further questions on this, now let's actually go ahead and really try and kind of clean up everything with the touchscreen sensor. Okay? So first, let's just kind of draw a reminder of what that whole circuit was going to, actually supposed to look like, right? So I believe what you guys have all been kind of looking at and analyzing so far looked something like this. So you had some current source, which now we actually have some idea of how to really implement. You had some switch, which I'm going to label as being S1 over here. We had the touchscreen capacitor, right? The CEQ, E1, E2. And then what we basically did is we connected that to some kind of op-amp circuit, basically to check whether or not the voltage that we ended up producing across that capacitor was above or below some threshold. Okay? And so this was like our sensor output over there on the right. And this was some VREF right over here. Okay, now, I don't know which direction, he connected the op-amp before. I'm going to connect it in this particular direction for reasons that hopefully will become apparent a little bit later. But basically, I'm doing it this way in that we know that CEQ, E1, E2, if you touch, is going to be larger, and if you don't touch, is going to be smaller. So maybe just to kind of check as a review, even for kind of the circuit that you guys were looking at before, well, maybe I should check. I assume you guys drew the waveforms of kind of what the voltage across the capacitor is supposed to look like, depending on whether you touch or you don't touch. Is that right? Yes, you did. Okay, so if you kind of zoomed in, and I believe you guys saw the current sources being periodic, if you zoomed in on like one of those periods, right, what you should have been seeing is something like the following. So let's say that there was a touch and the capacitor was larger. Right, so this would be the case with no touch, and this would be the case with touch, right? And, because it was periodic, you had it actually going back down. I should do it this way to be a little bit more accurate. Right, so basically, when you didn't have a touch, the amplitude of that waveform was larger, right? Like the peak point you actually would reach would be larger than the case where you didn't have a touch, okay? So here I'm just setting things up this way in that I'm going to be detecting basically whether or not this amplitude is above or below this line here. And if it's below it, I want to have the sensor have a positive voltage saying, yes, there was a touch. And if it's above it, I want to have the sensor have a negative voltage saying, no, there was not a touch. Okay, so that's just why I set the comparator terminals the way that I did. Which, as I said, I'm not sure if you sort of saw it the other way around, but this is the way that I set it up here. Hopefully, if you flip everything around, you just have to reinterpret what the output actually means. Okay? Okay, so this was our basic touchscreen sensor. What I want to do now is I want to sort of set things up in a slightly different way, just to avoid one problem, which we'll come back to a little bit later. But you'll see that, if you understand sort of how everything is working in the way that I'm going to set up, then it's really the same exact idea with the periodic current source as well. It's just going to be a little bit easier to talk about it this way. Okay? So in particular, what I want to do now is, I think the way you talked about it so far, you were sort of told, well, this switch here just is used once at the very beginning of time to make the capacitor have 0 volts initially, and then you let it go and you turn on the periodic current source, right? That was kind of the way it was thought. Is that correct? I don't see too many. Okay, there's at least one person shaking their head, so I'm going to assume that that is indeed correct. Okay, so I'm going to do things slightly differently. This time what I'm actually going to say is, let's take this current source. Let's assume it's actually just totally constant. Okay? So don't worry about the fact that it may actually be varying with time. Just make it a constant current source. All right? I'm still going to have this switch, S1. I'm still going to have the capacitor. I'm still going to have the op amp connected to it. So I'll go ahead and draw it, but it's not really critical for what we're talking about right now. Okay? Now what I'm going to say is, rather than the beginning of time or whatever, I just connect that switch. Every time I want to check whether or not there is a touch, before that happens, I'm going to turn on this switch S1. Okay? So in other words, and I'm going to call this taking a sample, right? And by taking a sample here, what I mean is basically your circuit is checking, is there a touch or not? So before I take the sample, I'm going to turn S1 on, which means sort of the equivalent circuit is going to look like this. And I'm not going to draw the op amp just because it doesn't actually matter in this case. Okay? So if you go and you just analyze this circuit, well, there's a short circuit here, so the voltage across the capacitor obviously has to be 0 volts. Okay? And if you're worried about what happens to the current, well, don't worry, right? That current just comes out over here because there's 0 volts and there's no change in voltage across the capacitor. All of that current just flows through here, and then that's where you have to remember that the grounds are actually connected, so the loop just goes to the ground. Okay? So everything is now just set up so that the voltage across the CEQ here is going to be equal to 0 volts. Okay? And again, if you don't see that, you're more sort of used to the linear algebraic method, you can go and work that out, but there's really just one node in the circuit, right? There's just a U1 here. If I put a short circuit between U1 and ground, that means U1 has to be equal to 0 volts. Notice that is also the exact same voltage across the capacitor. That's how I came to this so quickly. All right? Okay, so we're going to set things up that way. So now what I'm going to do is, when we actually want to take the sample, meaning we want to check is there a touch or not, we'll turn S1 off and let the circuit run for some time t. Okay, capital T here. Okay? So if I just redraw the circuit, now I'm going to have this IS, the capacitor, and of course the comparator out over there. Okay? So now life is pretty easy, right? I have just this IS, the current into the comparator is 0, so that IS has to flow fully through the capacitance. We know that for the capacitor, we just have that IS is equal to CEQ E1 E2 times dV, and let me call this, well, yeah, I'll call this VC, that's fine, dVC dt, right? That's just the equation for the capacitor. Well, if the current is constant, and this has some value, which is either the value with a touch or without the touch, then this is kind of like the simplest, let's say differential quote-unquote equation you can come up with, where, you have a constant that, has a time derivative, so you just take the integral. Hopefully, again, you guys saw this all before. This would basically say that VC as a function of time is just equal to IS times time divided by CEQ E1 E2, right? And so now if you let this run for some fixed time period t, that would say that at that time period t, you would just get IS times t divided by CEQ E1 E2. Okay? All of this should hopefully be a review. I just want to do it one more time to make sure that, things are clear here. Okay? All right, so the way this whole thing is supposed to be operating is basically as we showed in that original picture. If this voltage over here is basically lower than Vref, then that implies that the capacitor has some relatively large value. And if it's larger than Vref, then it implies the capacitor has some relatively small value. And then, if you're lower, then great. The output of the op amp is, goes up to VDD. And if it's lower, then the output of the op amp goes to whatever the negative supply rail is, right? And so if it's high, it's telling you there was a touch. If it's low, there was no touch. Okay. So why did I bother setting all this stuff up? Now let's see what happens if we actually use our current source circuit. Okay? So all I want to do now is redraw this whole thing, but using the current source circuit that we introduced before. Okay, so we have some VS, some RS. This is the op amp that we use for our current source. We now have the capacitor, right? That capacitor had some switch across it. And if we just follow kind of the same way we did before, we would have connected the op amp over here. Oops, sorry. That should be Vref. Right, and this is the CEQ, and that's the switch S1. Okay? Everyone see this? All right. Does this work? Does this actually detect anything? See a couple people shaking and or nodding their heads. Maybe we'll try and take a poll and we'll see how many people can get to raise their hand. So who thinks, well, yeah, we'll try it. Who thinks this does work? Everything is handy dandy. We built a current source. We plugged it in like we did before. Everything is great. Okay, my tone is clear enough. Who thinks it doesn't work? Why not? Why doesn't it work? We'll see if we can get somebody who hasn't raised their hand before. If not, we'll come back to those who have. Yeah? No. Okay, so almost. So notice this op amp over here, there's no feedback, right? So these two, they can kind of do whatever they want. Here we're actually intentionally kind of, we're connecting this op amp usually in this way, meaning that, the negative rail is ground and the positive rail is like some supply voltage usually associated with the thing we want to read out on the other side to have like a nice digital signal telling us if there's a touch or not. So it is, however, very much related to negative feedback. See, that part you had very much in the right direction. Yeah, right here. You basically said it. I just want to be much more specific. Yeah. I don't think the current here is going to change. I'm making Vs a constant for right now. Let's not worry about something more sophisticated. It's a constant. What did we say? There was two important caveats that we said when we used this op-amp as a current source, right? One of them was the negative feedback, which we've already checked. We've said if I connect a capacitor, fine, it's a negative feedback. There's this other one that I told you that was going to be subtle and that you were going to see what the problem was when you actually connected into the sensor. That's the one that's important. And all of you have actually been like basically touching on it, and you did actually basically say it. I just want to be really very explicit. So if I call this U2, what's the value of U2 relative to ground in volts? 0 volts, right? Okay. Let me explicitly write that down. U2 is equal to 0 volts. If that is 0 volts, does that depend on the value of CEQ, E1, E2 in any way, shape, or form? It doesn't, right? It's just 0 volts no matter what you do. No matter what the capacitor is, it's 0 volts because this whole thing is a negative feedback, right? So the problem is that if I try and measure a voltage here that tells me something about CEQ, E1, E2, that voltage is 0. It doesn't actually care what the value of the capacitor is. Okay, so this is why I said, again, there's one subtle problem you really had to be careful about with this particular current source implementation. This is what it is, which is you can't just go and try and read off a voltage here relative to this ground because it's always 0. It does not actually change. Okay? People clear on the problem? Maybe raise your hand if you understand why things don't work now. And who's still not so clear? Okay. Let me just draw things slightly differently. So for those who it's not still clear, this is kind of the inverting amplifier that you know and love, right? And you probably remember that this V out is equal to minus R2 over R1 times Vs, right? Well, what if I actually asked you to measure this? Let me call this V1. Just as a pure analysis problem, what is V1? And I'm going to try and see if I can get somebody who was, didn't see the answer before to actually answer this. So what is V1? Yeah. Yeah, it's 0 volts, right? Because just take this as an analysis problem, right? Golden rule number 2 says that V plus is equal to V minus. Oops. Well, look, V plus is equal to 0 volts. So V minus, therefore, also must equal 0 volts. Okay? Well, all that has to be true for this voltage here to be 0 volts is for the op-amp to be a negative feedback. Well, now let's come back and look at the circuit over here. If this op-amp is a negative feedback, well, guess what? V plus will equal V minus. U2, therefore, will be 0 volts. U2 is exactly the node that we're looking at over here in the comparator. So in other words, what we're saying is we're going to compare 0 volts against Vref. Well, depending on the value of Vref, that answer will always be the same and will not at all depend on the value of the capacitor. Is that more clear? If you were confused before, is that more clear now? Please try and raise your hand. Okay, good. Okay. So now that we've done that, how are we going to fix it? Yeah. Okay, so you said you could use a quote-unquote different ground on one of the circuits versus the other. That's kind of true, but I think there's an easier solution. Okay? And maybe I'll actually uncover this because that's kind of the hint. So in the inverting op amp, where did you take the output from? It's drawn on the board, so to speak. So, bingo. Okay, so notice in the inverting op amp, if people don't see it, I can redraw it. So we'll check that in a second. In the inverting op amp, this thing here is the equivalent of U2, right? Those are sort of the equivalent nodes from the standpoint of the configuration of the circuit, right? This node over here is this one, which is directly connected to the output of the op amp, right? In the inverting amplifier, we said that V out, right, this has some voltage. It's minus R2 over R1 times Vs. So this is allowed to move around relative to this ground. It's this one that's not. So in the equivalent thing over here, that would mean that we would actually want to take the output from over there, right, from the bottom side, quote unquote, of the capacitor, not from the top side, simply because the top side is the one that's connected in the negative feedback inside the op amp. Okay? So let's actually go ahead and really redraw that. So what we're saying here is that we're going to have a Vs, we're going to have an Rs, we have the op amp, we still obviously have the switch here because that's what's needed to initialize everything. We have the CEQ, and now instead of trying to take things from this top node, we'll just grab the bottom node and feed that into the comparator. Okay, so now I left a couple of things blank here somewhat intentionally. So first things first. Right, this was our U2 that we said was always going to be 0, and this is our U3. Okay? Well, back when we looked at kind of the simplified version of this circuit, right, just this kind of thing, we actually came up with an equation for what the voltage across the capacitor would be, right? We said that the voltage across the capacitor was equal to something like the current times the time divided by the value of the capacitance, right? Well, I claim this U3 also is directly related to this, but has one important change. What is that important change? What is the important difference? Yeah, it's negative, okay? Exactly. So U3 will be equal to minus VC. Right? And if we just define the VC that way, that's what I mean here. Okay, so if U3 is minus VC, that simply means that, now, and I'll go back to that picture we drew a long, long time ago. Hopefully I can find it relatively quickly. Yeah. Now that means that rather than having the output voltage of our sensor go up like this when we actually turn on the current source or really turn off the switch, now it just means the output will go down. Okay? And so if it's going down, what we're basically saying is we can essentially leave everything as we did before. Just double check I get this all right. No, not have too much stuff here. There we go. Now what we're basically going to say is that instead of comparing against Vref, we'll compare against minus Vref, right? And in fact, I think that other picture, I'll just draw it again in a second. And so now we actually will flip the direction, because what's going to end up happening is we want to check, is the thing lower than minus Vref or higher than minus Vref? Okay, and again, I think this will all be more clear in 1 second when I draw sort of the real picture. Okay? So in other words, what we're saying here is that if I was to draw essentially, I'll do actually two plots. So if I draw the voltage across the capacitor versus time, and I draw U3 versus time, as we said before, these are just inverted from each other, right? So right when you start, I have some constant current flowing through here. That constant current flows into the capacitor. So we'll get something that looks like this. And then at time t, if we stop, we would measure this value that we said right over there, which would turn out to be just Vs divided by Rs times t divided by the value of the capacitance. And so if we look at U3, it's just going to be exactly the negative version of that. So same thing over here. Now it's just minus Vs over R times t divided by the capacitance. And this is the time. Okay? And so to be clear, if I wanted to look at what happens when there is a touch versus there isn't, so when there isn't, the value of the capacitance is smaller. When there is, the value of the capacitance is larger. So if this is the one with the touch, for example, so this is with touch, and this is no touch, right? Then now what we're trying to do with that comparator circuit over there is just put a minus Vref somewhere in the middle over here, so that if there is a touch, it will be above that minus Vref, and if there is not a touch, it'll be below that minus Vref. Everybody good with this? Yeah. So it's just that, remember, and this is where this picture will be useful. This whole box over here is intended to mimic what this current source is doing, right? So if I look in this picture here, oh yes, sorry, thank you. If I look in this picture over here, right, the current source is pointing up, and this top node over here, which is the one that went into the comparator op-amp, that was like the quote-unquote top side of the capacitor, right? So the current was flowing this way, and that's where I would therefore have to put the plus of the capacitor, just again based on passive sign convention. Well, this box is this current source. Okay? So in other words, this whole thing should be replaced by a current source with the arrow pointing up. Okay, so that means there is a current flowing into the capacitor in that direction. Well, if it's flowing in that direction, the plus should be here and the minus should be there, once again by passive sign convention. But now notice U3 relative to ground, U2 is also ground, but the minus side is here and the plus side is there. So just by looking at it, because the signs are flipped, that's why I'm saying that U3 is equal to minus this VC. Make sense? It's a good question. More questions on this? Okay. So, by the way, maybe I should check. Have you guys actually done the lab already or not yet? Is that next week? Next week. Okay. Got it. All right. So, when you actually do get to the lab, you're going to see that life is slightly more complicated. And this is where sort of, some of the changes that I talked, or some of the reasons why I talked about it here, not necessarily as being periodic, are going to come from. So we'll see that in one, let's actually go ahead and get into that a little bit. Okay. So the version of things that you've talked about so far and that you will actually make use of in the lab, in that case, what you actually did was the following. So you have some VS. You're still going to have some RS, which again, this is just going to end up being our current source. We're going to have this capacitor over here, and then let's not worry about the comparator for now because it's not really kind of relevant or important for this piece of things, right? So in class so far, right, again, if I sort of treat this whole thing as being a black box, so far we basically said that, hey, with this IS, we were going to make it be some kind of periodic waveform, right? We were going to have it be something like it was going to be high for some period of time, and then low for some period of time, and then high for some period of time, and so on and so forth, right? So if I plot this IS, and this is T, you had something that looked like this, okay? And I'm going to label this as being some time period T. This should have been, well, I'll be careful. This would be T, this would be 2T, this would be 3T, and so on and so forth, okay? So in other words, there's a time period of T, of it being either high or low. And each one of them, every T, it changes between being high and being low, okay? So if we use this kind of setup, and this is really mostly review just to make sure everything is clear. If I was to plot this over here, this V out, what will that be? Okay, and by the way, just maybe I should have been even more clear. To get this kind of IS, notice the VS would now also have this same waveform, right? So if this is what IS is supposed to be, then to get this, the way you'd actually implement it, and this is what you will really do in the lab, you'll go and you'll take what's called the function generator. You'll produce a voltage that has this same shape of waveform, but its value will be picked such that you get the IS you want, right? So as a reminder, IS is just equal to VS over RS. So you'll pick some RS, and then you'll set the amplitude of that VS waveform to get the IS waveform that you actually wanted, okay? Okay, so again, if this is what you go and do, you take some VS, it has this kind of like, square-like kind of waveform, which would result in this IS, and let me label the IS over there. What will the V out of T actually look like? Yeah, exactly. So I see somebody making this sort of hand motion. It'll look like a triangle, right? Now, to be absolutely clear, when the IS is positive, what will the slope of the V out be? Positive or negative? Careful. Notice where the V out is. Okay? Yeah, it's going to be negative, right? Because notice again. Oh, yeah, thank you. Okay? If this is where the IS is, right, and it's positive here, this would be the VC. But notice the V out, I'm measuring down on the bottom side relative to ground. Okay? So it would be flipped over. All right? So in other words, and this is where I'm going to... This would mean that when this one's negative, the slope on V out is positive, and vice versa. Okay? So that's what this waveform would look like. Okay? Okay, so let's just pretend that I go and I let this thing run kind of, forever. It's just every T I just, have either positive current or negative current. And I just keep alternating back and forth between those. All right? So let's say that I went and I touched this thing right exactly at this time right there. Okay? How would that change the waveform? What should, if let's say the black is everything that happened before the touch, and now I want to draw in a different color what the waveform should look like after I touched. So what will that look like? What does the touch do? What does it change in this whole picture? Changes the capacitance, right? Okay, and maybe I'll explicitly write it out. This value over here, as a reminder, is just Vs over Rs, which is the current, times the amount of time that you basically allowed this to run, divided by the value of the capacitance, right? Okay, so if I change the value of the capacitance, in particular, I increase it, what should now happen to the waveform? Yeah, exactly. The peak will go down. Okay, your hand motion was exactly what I was expecting. Okay, so indeed, I'm still going to have a triangle, right? Because it's still just going to be taking current and dumping it on a capacitor. It's just dumping it onto a larger capacitor now. So indeed, that will be lower, right? This will do something like this, and this will do something like that. Okay? And if this is really what happens, then life is pretty straightforward. It basically works very much like we described before with the switches and everything, right? It's just, we would put some Vref as an example over here. And if you see that this waveform crosses the Vref, right, if we look at the output after the comparator, you would see that to be like a blip high here, indicating that, okay, well, or blip low, in fact, in that case. And, when it's below, then you're fine. Okay? Meaning you detect the touch based on whether or not you actually cross this reference level. All right? So that's all good, but now I'm going to make your life a little bit more painful. Who says I touch right at this time? Nobody, right? Okay, so now let's actually do something a little bit different. I'm just going to redraw the waveform because this is going to get too busy otherwise. So all I'm going to do is, again, just redraw that same waveform, assuming there was never any touch, and then look at what happens if I do touch, but at a somewhat different time. Okay, so now let's say, let's make this the original waveform, something like that. Okay, now let's say that I go and I touch, like, here. What's going to happen? Okay, yeah, so somebody made a hand motion which initially is absolutely correct. Okay, so I think the hand motion you did was like this. Okay, so it's absolutely right. This slope will get smaller, right? That is true. What's going to happen afterwards? Okay, it's going to go back down, also with a smaller slope, right? Okay, and I'm going to exaggerate things slightly. Let's say it only goes back down like this. Okay? And let's say next time around, it goes back up only like that. Okay, well, notice, depending upon where exactly you touched, now this thing looks kind of weird, right? Like before, at least, we always had these kind of like triangle things that, because I sort of chose where I touched at exactly the right time, I could basically just look at the amplitude of that triangle and life was good. Right, because everything was nicely centered at 0. Well, here now, depending upon where I actually touch, I basically have some history coming from, what happened previously when I was not touching. Okay, so this thing could end up, for example, moving around like this. Let's say alternatively you touched over there. Well, now maybe it's going to move around like that. And sorry, I did this incorrectly. There we go, like that. And so on and so forth, right? So now, depending upon when you touch, you're going to get a very, very different voltage. That's no good. Okay? Well, so this is where I'm going to invoke what, for all intents and purposes, I'm going to call black magic right now. It's not actually black magic, and you kind of almost know what you need to know to sort of understand why this is going to work the way it does. But to really understand it, take 16B. Okay? So there is a very simple fix for this. So the very simple fix is going to be the following. So if we take this original circuit over here, which was kind of our current source that we were intending to just have it dump basically current onto a capacitor, well, the simple fix that, again, this is what you're actually going to see in the lab, is just add another resistor over there. Okay? Now, as I said before, to fully analyze this, you actually now have to sort of be able to deal with real RC circuits. Okay, so that's not, technically something we're really going into here. But to give you a little bit of intuition as to what we are trying to do here, that does actually sort of fall, let's say, almost into the scope of things you've learned about. So my understanding from Vladimir is that, you did actually kind of go through and do analysis of, okay, well, like, if I just have a circuit with resistors and capacitors, and I'm just interested in, like, if I was to not do anything else, but just kind of like give everything a static voltage and wait long enough, you knew sort of how to treat the capacitor, quote unquote, at steady state, meaning that, like, eventually the capacitor just, sort of has no change in current across it, right? Which I think the simple intuition for this one is that in, quote unquote, steady state, the capacitor is a so-called open circuit, right? This is kind of, I think, what you guys were all taught, and I hope I don't see too many nodding heads, but I'll assume that everyone's okay with that, and if not, I'll sort of cover it in a second. Okay, well, so the idea here is that if I add this resistor in, let's assume for a moment that I want to look at just what happens over a very, very long period of time. And in particular, I want to pretend that, there's actually no variations in any of this. I just want to look at, on average, what is the behavior of this circuit. Okay? Well, if I look at the Vs, right, which again is going to have this kind of waveform here, on average, the value of Vs is 0 volts. Okay? Well, if the value of Vs is 0 volts, if I don't have this resistor here, and I'm just looking for things where nothing is actually ever changing, well, if nothing is ever actually changing, right, as we said, the capacitor is an open circuit. If the capacitor is an open circuit, well, actually you're not really in feedback on average, right? You're only in feedback, when you actually really make changes at the output, right? So all this resistor here is doing, when you add it back in, it's trying to make it so that, on average, this op-amp is actually in negative feedback. Okay? If it is actually in negative feedback, then, on average, the value of Vout should also be 0 volts, just because it'll be minus whatever this resistance is, let's call this some RL or something, divided by RS times Vs. And on average, we said Vs is 0 volts. Okay? So, by the way, just to be 100% clear, if everything I just said in the last 5 minutes or so doesn't make any sense, don't worry, that's completely not in scope for this class. Certainly not for, sort of the final or anything. I'm just mentioning it because this is a practical issue you'll run into in the lab. And so you may be wondering, well, why in the world is this resistor here? Well, understanding, why it is that these waveforms kind of look weird and could mess up the sensor, that's all in scope. This particular solution and why it works, that's the part that's not in scope. Okay? So that's something that you are actually going to see in the lab. And, so that's why I wanted to just kind of quickly run through it here. Questions on that? Yeah. Okay. So the question was, won't this RL somehow kind of interact with the voltage output and change the exact behavior that we're looking at? The real answer, of course, is yes. It will have some interaction with the capacitor that's there. The practical answer is that what you're going to do is you're going to try and make this RL, you're going to pick its value in a way that, given kind of the period at which you're operating this thing, the amount of current flowing through that RL will be very small compared to the amount of current flowing through the capacitor. And if that amount of current is very small, then, as let's say an engineer, this is where I say, well, if it's small enough, I'll just neglect it. Okay? As I said, to figure out exactly, sort of really how that would work and how you'd actually pick that value, and, what the implication on this time period would be, 16B. Okay, any more questions on this? Yes? Oh, okay. So the question was, why is it that, well, just to make sure, I want to make sure I answer the question you're really asking. So are you asking about why is there a slope period, or why is it that the slope is inverted, or both? Okay, yeah. So the question was, why is it that the slope is downward when, for example, the current here is positive? Okay. So remember, this waveform, this IS that I'm plotting here, is this IS. Okay, because this box is basically acting, did I lose it? Let me get my original picture back. There we go. So this box here is all replacing this current source, right? And so when I labeled IS over here as going this way, then just by taking this thing and replacing it with this box, this is still the IS over here. Okay? Well, if you follow a passive sign convention, the arrow has to go into the plus, right? So the voltage across the capacitor has to be defined this way. But notice, when I said V out, I'm measuring the bottom side of the capacitor, the ones connected to the minus part, relative to ground. Okay? So that's why when the current is flowing in this way, the voltage across the capacitor is increasing, but remember, this has to be ground. So rather than the top side moving up, it's the bottom side moving down. That's why it is that everything is inverted there. Does that make sense? Yeah. Yep. Okay. So let me take one. Your question is a very valid one, and I just want to try and answer it in the simplest way that I can. So when I say the current, quote unquote, has to be this way, what I mean is that I chose, for example, the current arrow to point that way. When I pointed it that way, the plus and the minus of the capacitor were then set by passive sign convention. You absolutely could have said, I'm going to arbitrarily define the direction of the current to be to the left. The plus and minus sign on the capacitor would be flipped. But what would happen is that when you then go and actually solve the circuit, the value of the current would be negative, and the value of the voltage across the capacitor would also be negative. Okay? So in other words, when we say that you can define things any which way you want, that is indeed always true. It's just that when you define things, if you then go and solve the solutions, if you picked a different direction than what I did, your solutions will all have negative signs compared to my solution. That's all. Physically, it will mean the same thing because, if I tell you, and let me actually just draw this, over here, and this doesn't have to be associated with capacitors. It can be associated with anything. Right? If I call this, let's say, VR, with plus and minus like this, and the current like this, if I take that same thing in the same circuit, but instead I labeled it this way, and I called that VR, let me call this VR1 and VR2, and now I said this is IR1, this is IR2. Okay, if you took this same thing, you put it into the exact same circuit, and you did all the analysis, all that would happen is that VR2 would be equal to minus VR1, and IR2 would be equal to minus IR1. Okay, but remember, voltage it's all a relative thing, right? So all that this statement means is that, right, when I say that VR1 has some value, let's say it was 1 volt, I just mean that this is 1 volt higher than this point is. Well, if I then say that this one is minus 1 volt higher, it's the same as saying that this side is actually higher than that one. Okay? So in other words, it's all the same thing. It's just if you define things the other way around, you'll get you'll get negative values, which means when you interpret it, you can interpret it as, well, okay, rather than keeping track of a negative value, you can just flip everything around, and that's all I'm doing. Does that make sense? Okay. I think we are out of time for today. If anyone has further questions, feel free to come talk to me. Good luck, everyone, on the exam.